So let's get started, guys. And good evening, everyone. And thanks for coming to this talk on F#. So my name is Yan Cui, and I've been working with F# in production and SQL for quite a few years now. So it kind of saddens me to see there's still a lot of, I guess, misconceptions about F# and functional programming in general, where often people tell me that, oh, you know, F# and functional programming is great in specific settings, such as when you're doing loads of maths or finance. Whereas from my personal experience, I know that's just not the case. Functional programming is great. They're very useful and can be and should be used to solve many different problems that we see in line of business applications. So from my personal experience, I've been working in gaming for quite a number of years until recently, and I've used F# very heavily to do a number of different things, including modeling domains, to write infrastructure code, game logic, algorithms, etc., etc. So until this year, I was working for a company called Gamesys in London, where towards the end of my time there, I was building backends for social games, and we had somewhere around 1 million daily active users, with the number of people that's installed, that's close to, I don't know, in the tens of millions. And from the million daily active users we get, we receive somewhere around 250 million requests per day. And pretty much all the requests are, well, everything you do in the games are recorded so that we can understand what people are doing in the games so that we can optimize them and improve them. And for that, we record somewhere around 2 to 3 terabytes of data just for analytics every month, which doesn't take into account all the data that we generate and maintain in order to facilitate your actual gameplay. And one interesting thing about gaming is that pretty much everything you do in the games is a write. So everything I do in the games is going to update my game state in some way. So we usually see 1-to-1 read-to-write ratio, which is quite different from the usual sort of read-heavy traffic that you see for web-based applications. And at peak, we see somewhere around 25,000 database ops a second. As for the team, we had a very polyglot team, both in terms of the languages being spoken, as well as the technology stack being used. You can probably identify a few of the databases that we were using, and we were very heavy users for both Amazon Web Services, as well as Google App Engine. And on the back end, we use C# and F# very heavily, and also did quite a bit of work with Erlang as well. And as for why F#, while most of the adoption has happened in the sort of finance space, F# on its own is a very versatile language that's good for great many things. And one of the things we found is that we can be a lot more productive since our switch to F#, and that's very important to us because with a very small team of 6 backend developers, we look after everything that happens on the servers, from writing the server-side game logic to building up the infrastructure so that we can scale to meet the demands we have. And we also have to do all the ops ourselves. We didn't have a dedicated ops team. And whilst we want to move fast, we do not want to sacrifice on the quality of the work that we produce. And we also found that F# is very good and can be used very useful to help us to write efficient, concurrent, and parallel code. And I can often find the simple solutions to otherwise complex problems. And as a company, we were doing a lot of both real money as well as social, casino, and slots games. And I personally built quite a number of games in the backends for a number of games in the F#. And one of the more interesting games we had was this game called the Monopoly House Party. If you haven't played slots game before, don't worry, most of you haven't. And in fact, myself, I haven't played any slots at all until I started working for Gamesys and ended up building all these backends for social slots games. The mechanics are very simple. You decide how many coins you want to bet on each of these 25 lines in the game. And then when you press spin, it makes the server call. And then all the symbols are going to spin around. And then when they settle down, if you've got the number of matching symbols that are here on the same pay line, then you win what is called a line win. And in this particular game, and in most other games, you also have a wildcard symbol that can substitute for other symbols as well. And for this particular game, you also have a bonus symbol, where if you have 3 or more bonus symbols anywhere on the screen, so you don't have the 4 on the same pay line, then you also get what is called a scatter win. behind the scenes for every game, there's actually a math model which governs the likelihood of your winning and how much you're going to win based on different combinations. So we know for a fact that over the long term, players is going to win 95% of their wager back, which means the house always keeps 5% all the time. So remember that house always wins. So to model this game and other games like this, we have the first model what are the different symbols that we can have, which is either a standard symbol or a while symbol. So this is what is called a union type in F#. It's kind of similar to enum in that you can have different cases, but unlike enum, each of these cases is a full-on type. So you can't just create an invalid value by casting 42 to your enum type. And each of the cases can be associated with an arbitrary set of types. In this case, a standard symbol have to be instantiated with a name for your symbol. And a while symbol is just what it says on a tin. We can use union types and model different wins you can have as well. For instance, a line win is just you need to know the pay line number, the symbol that you won with, and how many of symbols that we actually have. And for scatter win, because we don't have to consider the pay lines, so you just need to know the symbol and count. And when I model my domain, I don't like to see things like integers and strings all over the place because they're very generic and doesn't really tell me what those values represent. So what I typically do is to use type aliases to then help surface my domain through my types. And one of the nice things about union type is that unlike a class hierarchy, which is always open for extension via subclassing, so whilst I'm working in a local scope, I can't tell what are the future subclasses that's going to be created. But with union type, I create a closed hierarchy of only the states that my system can have. And when you're working in F#, you don't have the null to deal with, which is the #1 invalid state that everybody spends time dealing with all the time, which is why Tony Hall actually calls them his billion-dollar mistake. And if you hang around with functional programmers, you often hear this particular phrase being repeated all the time, that we want to make illegal states unrepresentable in our model, so then we don't have to spend more time dealing with them later on. On that topic, you can also have this feature in F#, which is very useful, called union of measure, whereby you can have a type that represents some unit, and you can decorate it with the measure attribute. And from then on, you can then use that to add contextual information to numeric values, the way you can use them in like generics. So 42 is no longer just a normal 42, but you can attach it with some units. And out of the box, F# handles a combination of units correctly. So if you have 10 meters divided by 2 seconds, the value you're going to get back is not just 5, but it's 5 measured with the unit of meter per second. Similarly, 10 meters times by 10 meters is going to give you 100 meters square. But if you try to combine incompatible units together, then you get compile time error. It's very useful too because it gives you much stronger static safety with regards to the use of numeric values, and you can use that to help model your domain to help prevent invalid states from creeping into your the part of your calculation. For example, that works out how much should we pay out to the player in terms of wager amount, which in this case has to be a long that's measured in pence. And again, you can see that I'm using type aliases to help surface my domain through my type signature. And to capture the whole state for the game, I can use what is called a record type, which is a very lightweight data container type where the fields are immutable by default. And this was one of the more complicated, more complex slots games that the company has ever done. It was delivered on time, performed really well, and we had 0 bugs reported over 2 years since of the game being in production. So to recap, with the union types and records, you can have a very lightweight syntax for describing, for creating types as well as hierarchies. They are great for modeling your domain because they allows you to clearly and concisely express your domains through types. And because you don't have to deal with nulls, and because discriminant union types can help you create a closed hierarchy of only the valid states the system can handle. It helps you eliminate illegal states from your domain altogether. And with union measure, it helps enforce correctness with regards to use of numeric values. And from our experience, compared to an existing Java solution we had for the real money gambling games, we had switching to F# as implementation language gave us an easy and order magnitude increase in productivity. So where we had previously a team of Java developers maintaining a bunch of, working on the old game engine, and it would take them sometimes weeks to produce a new game, for the F# engine, taking into some of the learning that we had, as well as the language being able to give you more concise way of expressing the problem, sometimes I can push out a new game in a matter of hours or a day or two. And that was our first foray into adopting F#, and it was a big win. And from then on, it helped us to use F# in more places. Apart from social slots games, we also make a number of different other games, a number of games in other genres, including a softcore MMORPG game called the Hippie Monsters. And the interesting thing about this game is that we had tons of content. Just in terms of the dialogue between you and the non-playable characters, we have more text than the first 3 Harry Potter books combined. And where you build this virtual world, where people can go around, travel, and collect things, you find that people do that an awful lot, and their stage gets really big. In fact, we find that it's quite common for our player state to go into several megabytes after just a few weeks of gameplay. And where your player states are so big, the stateless approach doesn't work anymore, because you're shifting all your load onto the database. And this approach becomes very slow and inefficient given the size and number of writes that we are doing. Remember, we typically see one-to-one read-to-write ratios. Even though we were using pretty scalable key value stores already, which if you read all these benchmarks, they can do tens of thousands of operations a second on commodity hardware. But it turns out all those benchmarks are done with very small payload. And when you have real-world payloads that are in several megabytes, the actual number you're going to see, the actual throughput you're going to see are much, much smaller. And once you take into account the need for redundancy, then the whole sort of setup became quite expensive, because you need to run at least a couple of quite big, sizable nodes. And through profiling, we also find that the game servers themselves were spending upwards of 90% of CPU on serialization, deserialization. So if we had continued down the same path, we would just be throwing money down our AWS account, which of course they'd be very happy, but it's not going to be great for our long-term economic health. So when with games like this, one of the things you find is that the player activity is also quite bursty. Player will come in, they'll do a bunch of things, and then they will catch a few monsters, they'll plant a few trees, crops, and whatnot, and then they'll go away. They may not even come back until the next day. So you can actually take advantage of that and move to a stateful approach, whereby you can cut out most of your database calls, as well as all the associated serialization costs on the game servers. And for us, we were even able to fall back to using S3, because we only need very simple key lookups. And S3 is very cheap to operate, and it's great for storing large objects. It also has support for auto-versioning, and as well as lifecycle management, so that you can automatically archive the old versions of player state onto Glacier, which is an even cheaper long-term storage solution that Amazon provides. And because the way we have set up our stack, where the sort of state management is the middle tier, so that we could replace the stateless one with the stateful implementation without changing any of the game's logic. And internally, the stateful middle tier is implemented using F# support for actor model. And the actor model is something that's coined by Carl Hewitt back in 1973, and was later made popular by Erlang. And it's a model for describing computation, whereby everything is an actor, and an actor is the fundamental unit of computation that consists of the 3 things: processing, storage, and communication. And this model, everything is an actor has a mailbox, they share nothing. They don't share any memory, and the only way for actors to communicate is via asynchronous message passing. And inside the body of an actor is inherently stress safe because messages are processed one after another in a single-threaded fashion. So you don't need to use very heavy kernel-level constructs such as logs and mutex and whatnot. And when the actor receives a message from his mailbox, he can create new actors, he can send messages to other actors he knows about, or he can do some work, or all of the above. And in our particular setup, we have two types of actors. A worker whose job is to manage the different pieces of state for a particular user using optimistic locking. And if the user has been idle for a while, it would also then persist the player state in the background. There's also a gatekeeper whose job is to keep a list of the active workers on the machine and then spawning new ones when the new player comes on board. So in this moment in time, we have workers for player B and C that's live on this machine. Player A makes a request, and through the request handling code, a request was sent to the gatekeeper, who then sees, okay, I don't have a worker for this player, so I'll spawn a new one. And as part of his initialization, the new worker will then fetch the player state and then respond to the request calling code directly, bypassing the gatekeeper, because in this particular setup, the gatekeeper is a potential bottleneck, so they want to reduce the number of messages that have to flow through the gatekeeper. In the meantime, worker B sees that his player has been idle for a while, so then he will persist the player state synchronously in the background, and provided that that was successful and that the player hasn't made a new request in the meantime, it would then tell the gatekeeper that, hey, my job is done, and then it will shut itself down. And the next time the player B comes back, then the gatekeeper will say, hey, your guy is gone, and you will respond with a specific error code so that the client knows that it's time to go back to the load balancer to find another server to talk to for the duration of this new session. And we do this so that the load is distributed across the cluster, and we stop players from hogging a particular server so that we can still scale down our cluster of machines elastically. I mentioned earlier about F# support for the active model. It does it through this mailbox processor type, which for some reason everybody in the community always aliases to agent. I don't know if what reference that is for, but everyone seems to do it. And notice that agents are typed, so you have to specify what messages an actor can receive. And for the workers, our messages we can send two messages, two types of messages, either a get for the current state of a given player, or a put to update the current state with version control. In both cases, we need to pass in an asynchronous reply channel, which is a mechanism for us to then send response back to the caller, and they can wait for it asynchronously. But we still need to decide what types go into those reply channels. Well, we need to tell you whether or not the operation was successful, or if it failed. And if it failed, then what exception was thrown. So we can capture that with a very simple union type that captures both the success and failure case. So for get, the response will contain the player's current state and version number. And for put, which returns unit, which is the sort of functional language way of saying void. So that completes our definition for the message type. And as for the workers, they need to know the unique ID for the player whose state they're managing. And every worker can be in either one of two states, which is either working or closed. And when it starts up initially, it's going to get the player state, and then it's going to go into the working state with that as version 1. And when we're in the working state, we have this async block. Inside of the async block, we can then use we can perform asynchronous operations and bind the result with the let bang keyword. In this case, this is how you can do non-blocking I/O in F#. And C#'s async await keyword was heavily influenced by the design of F#'s async workflow. The one big difference is that in C#, the language feature is async await, which means that the mechanism in which it's implemented, you can't extend it yourself, or you can't borrow it to implement something else. Whereas in F#, the actual language feature is called computation expressions, which for which is something that you can sort of leverage yourself to create other type of workflows. Async workflow is one instance of one implementation using computation expressions. And there's these guys in the F# space called Nessos. They actually build a framework whereby instead of having an async block, you have a cloud block. And everywhere you can say let bang some variable equals some asynchronous operation. That operation, instead of being queued to a thread pool, is queued to the cloud and it currently supports both Azure, and there's alpha support for AWS as well, which means that whenever you say you're doing some heavy computation work, you can offload all the computation to the cloud, to some cluster machines that you have running, but programming as if everything is running locally. And that's one advantage of having the computation expression being the language feature that you can leverage yourself and extend. And there's also other computation expressions that you can implement. For example, if you're coming from Haskell and you want to reenact some maybe monads and state monads, you can do the same thing with computation expressions as well. In this particular case, we want to wait for a message to arrive in the mailbox for up to 60 seconds. This particular method returns an option type, which is either some value, some message that we received, or none if no message was received after 60 seconds. And that's our cue to then go and persist the player state asynchronously, because remember, do bang, that's when you do an asynchronous operation. And after that, we go into the close state. If we did receive a message, then we can apply pattern matching. Remember, the message can be either get with a reply channel. So we can look at that, and then we can apply the pattern so that the reply channel is captured in a reply local variable that we can then use to send a response back to the caller before recursing with the current state and version. The message can also be the put message, in which case we can use pattern matching to get the new state, the version number, and reply channel back. And additionally, we can say that this particular pattern will only match if the version that's passed into the message matches the current version that we know about. This is how we can do optimistic locking, so that if two concurrent requests is received for the same user, the first, and they both do a get for the current user state, the first put wins. And with that, we can recurse with the new state that you passed in. We increment the current version so that the second put will fall into the next case, which is, okay, sorry, you tried, but you were too late, so we respond with a version mismatch exception instead. So with pattern matching, that's also a very powerful way for you to handle all your branching logics very concisely and clearly. And once we're in the close state, we just blankly reply with the worker stopped exception, because we no longer, the worker is done his job, is now in the closed state. So with this stateful approach, we found that we got at least 5 times more efficiency improvement, meaning that the same server can handle at least 5 times the number of concurrent requests versus the previous stateless approach. And we also managed to cut the average latency down by over 60%, which was the drop was even higher by the time you look at the 95 and 99 percentile latency numbers. And importantly, we were able to cut out all the database nodes that we had to run previously and just use S3, which is much cheaper. And combined with the efficiency saving on the game servers, we managed to cut the operational costs down by over 90% and actually made the game economically feasible to run at scale. And this was another interesting use of F# and the important sort of part of our journey. But it's worth mentioning that this work was done in late 2011, early 2012, where a lot of tools that's available now wasn't available to us back then. So if I was to do this again, I'll probably just use something along the line of Akka.NET or Microsoft or Linux, which has got this concept of virtual actors, which is very powerful, very, very interesting. Or if you're more adventurous, feeling more adventurous, and happy to step out of the .NET world, Erlang and Elixir are also both very good choices as well. And staying with this game, we also have a very interesting achievement and quest system whereby you can pretty much hook into anything that users can do in the game. So for example, if a player caught a gnome, then he's going to get some XP, he's going to get some items, some gold, and he's going to make some progress on a quest. And by getting more XP, he might level up. And by making progress on a quest, he might complete the last thing they need to do on a quest, and therefore complete that quest. And completing a quest is going to give you more XP, more item, more gold. It's going to unlock any follow-up quests you have. And leveling up means more items, more gold, and more quests, and so on. And the whole thing also then feeds into the achievement system, which again, if you complete the achievement, you get more item, more XP, more gold. You get a drift. So this system was great for our game designers because they can hook into all these little things, and they can make a quest that requires users to go to London, buy a gold from Mr. McDonald's, then use that gold to then catch some monster somewhere, and take the loot drop, then take it back to Uncle Bob in New York. So there's all kinds of interesting things you can do. But for us developers, it was quite a big challenge. For starters, we have more than 100 different actions you can do in the game, most of which is going to give you some reward at the end of it. And all of that have to be, all that process, all that cyclical relationship have to be processed in the same request handling, so that the actual action you perform, which is catching a gnome, everything else that comes after have to be processed within the same request, and then at the end of it, we return the delta in the player state in the request to the clients, in the response to the client, so that we don't have to return a couple of megabytes of user state every single time. So that made my life quite difficult, partially because we have quite a number of different abstraction layers for different parts of the games, for traveling, for leveling up, for fishing, catching monsters, and so on and so forth. And then there's also non-functional requirements for tracking analytics, and if the users come from app partner, such as Nanigans, then we also want to inform them when the players have reached some milestone, such as completing the tutorial, reaching level 10, caught their first monster, and so on, so that they can then optimize the algorithm on their side to improve the quality of the player they bring into our games. So that made my life even more difficult. And we ended up with all this spaghetti code, which is just crazy. It was really hard to reason about because everything kind of depends on everything else. And the solution we ended up with was heavily inspired by the message broker pattern, which is an architectural pattern that we simply applied at a lower level. So whenever something interesting happens in the game, we record it as a fact, and that fact goes into a queue that's specific to that request that we're handling. And every flag is then presented to a number of different processors that looks after different aspects of the game, which may just ignore them, or it may do something interesting with it. And as part of processing, it may cause other state changes, which are then recorded as facts, and they all have to be processed by all the everything else, and so on. Okay, that's quite a lot of animations. For this system, we actually look at a number of different options, including a complex event processing system. But the purpose and the scope of the events that we are dealing with here are quite different in that they're limited to one request for starters, and what we needed really is a mechanism for linearizing what is otherwise a spaghetti program flow, which is why we ended up with a tailored solution that, in hindsight, was actually quite easy to implement and maintain. The one downside is that we needed lots of different facts to represent everything that can happen in the system, for all the actions that can be performed, as well as all the resulting state changes that can happen from those actions. And if I was to implement this with a class hierarchy, then I could have easily end up having to write hundreds of classes, which of course is no fun whatsoever, and not to mention all time consuming as well. So I ended up writing them, representing them as a union type. Of course, when you have a union type that's got 100 different cases, that's no more manageable than the massive class hierarchy. So what you typically do in this case is you break it up into a smaller, more specialized union types, and then you nested them with a top-level union type. And this would be the idiomatic way of doing things in F#. And the one on the processing side, you just do pattern matching. And then you can also break up your processing code into smaller and more specialized chunks as well. But because we have lots of our code written in C# as well, and we do an awful lot of interop between C# and F#, and when you're in C# trying to create a nested union type, it doesn't read really well at all. And in fact, as your union type takes a few parameters, this becomes more and more unreadable very quickly. So we ended up making a compromise and decided to go with a marker interface instead, so that all the specialized union types would implement the interface IFACT, which is just a marker interface that just helps us to identify and sort of unify our processing code. So instead of doing what we did before, we just replace it with a type test, which is what this operator does in the F#. But because we're not using a top-level union type, so we don't have that close hierarchy anymore, which is why we now also need a catch-all in case someone adds a new type of fact which we don't know about at this point. So even with the compromise, we still find the solution to be pretty simple and quite to reason about and understand. And it was very easy to add and remove, to add and modify existing facts where you just follow the compiler errors until you fix all the problems, or to introduce a new type of facts. And it probably saved me easily days or weeks in terms of the effort to create the class hierarchy as well as maintain them going forward. And as the name of the game suggests, monster trapping is a big part of it. And inside the game, to catch a monster, you have to be in the right place, and you have to use the right combination of bait and trap, kind of similar to what you do with Pokemon Go nowadays. And in the game, you have what is called an almanac, which is like an in-game Wikipedia where you can look up all the items as well as monsters. So for Bigfoot, we know that he exists in North America, and you need to use a particular bait with some chance of attracting Bigfoot to your trap, and you have to use a particular trap with some catch rate, which then raises another challenge of how do you automate the process working out of tuning the trap and the monster so that you get the catch rate that you're after. Both monsters and traps have a set of stats points that we use to calculate a catch rate between them. And then the formula also takes into account other factors, such as some traps are strong against air monsters but weak against water monsters. And then you also have seasonal monsters that can only be caught using the matching seasonal traps. And it used to be that our game designers would do this by hand via trial and error, which of course is laborious and also error-prone. And barring some miracle, you're never going to find the optimal solution. And when you have a system that requires people to do so much work by hand, via trial and error, what you're doing is you're hanging those people out to dry, because as Brian Hunter pointed out, said very nicely, that if you've got systems that require constant diligence, you're just setting everyone up for failure and hurt, because people are going to make mistakes. That's just what we do. And also, that's just not how they should be spending their time. So instead, we build a bunch of genetic algorithms and expose them as a web tool, so that the game designer can then go there, set up, okay, for this monster, I want to have this for this trap, and I want to have 85% chance of catching the mermaid, and then 75% chance of catching something else. And then you specify some settable error margin, and then just press a button and then wait for the answer to come back. And behind the scenes, we implemented the genetic algorithms, which general terms means when you start with a generation of possible solutions, each of them then goes through a selection process by passing them through a fitness test. Those that survive the fitness test are then put through a mutation process to generate a new generation of potential solutions for the problem. And you repeat this until you either found a solution or you've exhausted the maximum number of solutions of generations without finding any suitable solutions. In our particular case, we take for a particular particular trap, we start with some guesstimate for the stats, and then we will mutate each of the stats points with a small amount, so that when we are close to the optimal solution, hopefully we get something that's slightly better. And we also mutate each of those numbers by a large amount so that when we're far away from the optimal solution, hopefully we get something that's different enough so that the difference doesn't get swallowed up by rounding. And we keep doing this until we either exhausted the maximum number of generations we are allowed to run, or in which case we return the best solutions we found, provided that they meet the acceptance, the acceptable error margin, or if none of the solutions in the new generations survive the fitness test, in which case we just say, sorry, we can't find the answers based on your criteria. And the fitness test is as simple as the solution is better than the one that it was mutated from. And I mentioned earlier that we use Amazon Web Services very heavily, which also gave us some of the insights into some of the complexities that can come up as you integrate with many of their APIs. And we found that F# was a very effective weapon in creating DSLs to help us tame those complexities. For example, Amazon has got a CloudWatch service, which is the monitoring service where you can publish and collect metrics, you can set alarms, and by default, you get a bunch of metrics for your EC2 instances, such as CPU and network in and out. And you can also publish your custom application level metrics as well. And there's a management console we can go to, and you can select a bunch of metrics, chart them on a graph, and so on and so forth. It's an important service in the AWS ecosystem, but there's a number of shortcomings, including the lack of ability to find correlations automatically. So if you want to find if two latency spikes is correlated to each other and find the root cause, then that's kind of down to you to then go through all the metrics and then identify those correlations yourself. So if someone were to come to you and ask, why was the payment service slow last night? Which could be because the database was slow, because some other service that we depend on was slow, and maybe Stripe was having a problem with the API, for example. You then have to go around and look at all those, go through all the relevant latency metrics yourself to try to find that correlation. And when you turn routine post-mortem investigations into an exercise of finding a needle in a haystack, it becomes what I call a pain-driven development. And which is why I eventually, after doing this so many times, I decided to just spend a weekend and wrote a couple of DSLs to help automate all of this work that we tend to do by hand quite often. So that to say if you want to find out the 5-minute average metric, some metric for whose 5-minute average was more than a second anytime over the last 12 hours, you can then express that as an internal DSL, which is very human and readable, or equally, you can express that as an external DSL, which does exactly the same thing. And if you were to find out if any of your Redis clusters had a CPU spike, you can also just use regex to match against the metrics by their namespace as well as by name. And in total, we had I think 15 different operators based on what I can reasonably do with the API. And the internal API, the DSL was implemented in about 25 lines of code with some supporting functions to execute against the CloudWatch. And then I wrote a parser for the external DSL using a feature in F# called active patterns, and which was a bit more involved, but still wasn't a lot of code. And the nice thing is because I was able to use a type system to guide me along the way, so the first time my code actually compiled and ran, it did exactly what I wanted it to do, which was great. And now that I'm working a lot with Node.js, frankly, it's a feeling that I've been missing quite a lot. And it was, in this particular case, it's also great because I started to work at 2 a.m. because I had a bright idea at the wrong time in the day, and I managed to finish everything and go to bed after 4 a.m. And when I showed it to my workmates afterwards, they said, "Wow, you type really fast." But really, using the right tool for the job in this case has really helped a lot. And F# is, in general, is just amazing, and function programming in general is amazing for writing DSLs with, and DSLs and parsers with. And for this particular piece of work, the internal DSL can be used in anywhere where you can run some F# code. It could be in the repo, it could be an executable. And the external DSL is useful for building tools so that I can package them up as a CLI and just give it to my co-workers who can then just write some queries and then run it and then plot some charts. Get some water. And so to recap, we saw how with Amazon CloudWatch, how its impedance mismatch renders routine post-mortem investigation into an exercise of finding a needle in a haystack, and how you can use F# to create simple DSL to at least make that needle a little bit bigger and easier to find. Another very popular service that Amazon has is called the DynamoDB, which is a managed key value store that has got built-in redundancy of 99 guarantees. And everything runs on SSD, so you get great and predictable performance, typically in the single-digit millisecond range for both gets and puts. And unlike most of other services that Amazon provides, with DynamoDB, you name your throughput requirement up front, and then Amazon would reserve enough capacity to service your the throughput requirement that you've specified. So you can easily scale to have a table that can scale to support millions of reads and writes a second with just a few button clicks. And you can change your throughput requirements on the fly without any downtime. So it's great because you just don't have to worry about scaling your database anymore. And because of the way it's charged, it's based on based on the throughput requirements you have for the duration you need them. So there's some interesting patterns that came out. I heard for this advertising company that for pretty much most of the year there's very little traffic, but then for the 4 hours of Super Bowl, it spiked to something crazy, like I think 2 million reads a second. And instead of having to maintain a super scalable infrastructure, and only to use it for that 4 hours and then just have that go to waste for the 99% of the time, you can just scale up your DynamoDB throughput for that 4 hours and get the whole thing over and done with a few thousand bucks. And so DynamoDB is great. It's amazing to work with. And for the last couple of years, I've been working with them. There's really had one big outage. But the one big downside is that even though there's a built-in support for queries and full table scans, to do them with code is kind of clunky. You create this request, this query request where you set a few parameters for the table names, et cetera, and then to express your query, you have to create condition objects and then set attribute value objects and then set comparison operators and so on and so forth. So even though you're not really writing a lot of code, but by the time you read all of that, you kind of forgot what was the question that I was trying to ask in the first place. And wouldn't it be nice if I can write something more like SQL, which is much more expressive of what I'm trying to do with the data? And so with that in mind, I sat down for another weekend and created another DSL to give me just that, with the aim of disguising some of the complexities that comes with the query and scan APIs for DynamoDB as well, which contains lots of different tweaks and options that you can set, and give my developers a query syntax that's very similar to SQL, so that's something that they're familiar with already. And the way it works, you say you take the query and then you pass it into an abstract syntax tree, which you can then use to actually transform to the request object that we saw earlier, but without you having to write them by hand. And to do this, to implement this DSL, I used the fparsec, which is F# port of the parser library from Haskell. And it calls itself a parser combinator library, which sounds a bit weird until you understand what it actually means. But all it is that you start with very simple parsers for simple things such as quote is a string in quotes, or single quote, double quote, or floats or integers. And then you have functions that can compose them together to give you more complicated or more powerful parsers. And those functions are called the combinators. So you do this iteratively to then build up a parser that can pass the keywords to the table names, to the attribute list, et cetera, et cetera. And then you can then build up a fully fledged DSL for managing a more complicated query syntax. And so with that, I was able to turn what I would have to write otherwise into something that's much more expressive and easier to understand. The query syntax took less than 50 lines of code to write, and which again just shows the amount of how much productivity gain you can get using the right set of tools for the job. We're doing on time, we're doing okay. And finally, we use S3 an awful lot. And one of the features of F#, a very powerful feature of F#, is this thing called a type provider, which gives you typed access to external data source, and it does all the type generation for you, both at design time, so as you're working and coding in your repo, in the IDE, as well as the compile time and at runtime. And so that because we use F3 a lot, notice that at the top I've got a type that represents my S3 account, and then another type that represents a bucket in my account. And every time I press dot, what's happening here in the IDE or when I run my code in the F# repo is that, hold on, let's wait for the dot. Okay, what happened there is it's actually making a call to S3, and based on the data, the response that comes back is generating types on the fly so that I get IntelliSense for my account in S3 and all the buckets and objects that I have there as well. Which is very useful. It means that instead of having to leave my IDE to use some other tool to download the files I need from S3 and then go back to Visual Studio or somewhere to then write some code to parse it, read it, I can just do everything from within the comfort of my repo. And where you have a bucket that's got a lot, millions and billions of objects, you can also use a search as well. Here I'm creating a type that represents a search in S3 by prefix. And again, when I press dot, that's when IDE is going to make a call to S3, and based on the result of that search, creating types on the fly for me. So it's great because now I get the IntelliSense over some external data source I've got, and it helps me remove all these magic strings from my code as well, and I don't have to wait until runtime to find out that some objects in S3 that my code depends on is missing. So the first time I find out is when I'm writing the code, because I only get those objects back if the object exists in S3 in the first place, and then every time I compile my code, the same checks happens. And also, I don't have to, even though there's all kinds of code generations happening, I don't have to manage them myself. So the sort of typical problem you run into with T4 and other code generation tools is, well, what happens if you want to make many modifications and you have to remember to press, and every time someone regenerates that code, all your manual changes are gone. You don't have to worry about all of that yourself. And because the types that are generated are erased to the object type at runtime, so you can easily scale to having millions of types without blowing up the CLR. And this is something that I built myself because I use S3 a lot. So, but there's also other more useful type providers out there for, say, reading XML and JSON files, so that instead of having to create your type, inspecting the JSON file, create a type that matches the structure you're looking for, and then write some code to read it and parse it, you just let type provider do that for you. Point it to an example data, say XML or JSON file, so that it trains the type provider on what sort of shapes those data are going to be, and then you can use the type that you've created to read from other sources. So an example would be if you point it to some JSON file you've downloaded, saved locally, and then once you've created the type provider, the type that can parse that data, you can then point it to the real data source you're looking for. There's also type providers for reading from SQL, as well as type providers from to let you use, and I kid you not, functions that are written in R or Python, so that if you're doing a lot of data science, it's great because instead of reinventing all those functions that you get from R, you just use whatever's out there. So that all this gplot and other things that the R gives you, which is great, but R is a terrible programming language for doing everything else. So you can do everything else in F#, but then still leverage the things that the R community has already developed with the help of our type provider. So that's the sort of a tour of some of the things I've done with F# in production the last couple of years. And I hope by now you've seen a glimpse of what you can do with F# beyond the basics. And again, like I mentioned earlier, the drive for us was really mainly around productivity and being able to write more correct code. And in the case of for a concurrent and parallel code, also write very efficient code using async workflow. And help us solve some more complicated problems. So things like DSLs are usually quite considered a hard problem in many languages, but for in functional and F#, so functional languages and F#, they're really easy to do. So with that, thank you very much for listening. Sorry, I was speaking really fast. I'm really jet lagged right now. Have you guys got any questions? Okay, yep.
So you said using F# increased your team efficiency.
Yep.
I don't think you really explained why. I would really like to know why.
Sure. So one of the things with the F# type system, for example, is more expressive. So one of the things I touched on earlier is the ability to define to express a closed hierarchy, and that's one of the dialogue with the compiler that I don't have with the class hierarchies. And because the syntactically, you've seen how I can use 2 lines of code to really express what is the 2 separate classes in 2 separate files. I can condense that to just 2 lines of code in the union type. And in general, in F#, you just don't have as much ceremony as some of the syntactic noise that you generate systematically, say, with C#. There was a guy called Simon Cousins whose company so he works for the energy sector, where his company implemented a bunch of energy contracts. And the C# project, I think, had at most 8 developers, and they spent something like 3 years without implementing all the contracts. And it took so long that Simon one day decided, I wonder how long it would take me to do this in F#. And he managed to do, I think they managed to implement all the contracts in under a year with at most 3 developers, and only Simon had ever done any F# in the past. So that's a good sort of empirical evidence of some of the productivity gains that I was talking about. As to why, I think when you're programming in C# or Java, you're not just programming in OO, but by and large, you're also programming in imperative. So by definition, imperative is you tell the computer what to do. So imagine you have to do that for SQL. You have to tell the SQL server how to query data every single time. It's going to take you forever to do whatever you want to do, rather than using a more expressive language to say, this is what I want, you work out how to best do it. So by going to the functional world, you're moving yourself up the sort of abstraction level, which means you start thinking more about what it is you're trying to do rather than how to do it. I think in terms of the productivity gains, that's probably where that comes in more often than more than anything else. There's also the sort of less typing because of the more concise syntax, but it's more the sort of the approach that I find is what gives me more productivity. Okay, question there.
Hi, you said right at the start that you had a team of Java developers before you went to F#.
Yep.
So I was wondering why you didn't go to a functional JVM language, especially since you're using Amazon as well, rather than switching to the .NET framework.
So the interesting thing here is that because Gamesys as a whole is quite a big company, so my team works on just social games, so games that are not real money gambling. But because we had a company that's been building real money gambling, real money slots games for a long time. So even though my team was running a completely different stack, that's mostly based on .NET and running in Amazon, we were able to sort of get our product out there. We decided to just leverage the intellectual properties that the parent company has invested in and built over the years, which is this Java-based game engine, rule engine for the slots. But then what we found is that whenever we need a new game or some changes from those guys, it takes them a very long time to turn things over. And a new game sometimes, like I said, takes weeks to implement, which is why on the sort of social space, we need to do releases very frequently because while players have a very short attention span, we need to give them new content on a regular basis. And in fact, we are doing a new slot game for every sort of venture we have every 2 weeks. But it means that we really need to get the server side of things done quicker so that the client guys can then have something to do the development against. And we ended up rewriting, writing something from scratch as a demo for using F# because I've been using F# in my spare time for a while, and this seems like a good fit for the problem. So I did that over the course of I think maybe a week or two, from having nothing to having something that's demoable and can be presented to the rest of the team as well as other people. And from then on, now I think by the time I left the company, we had something like 150 games implemented in F#, and everything was done by, I kid you not, someone I hired from out of university who knew nothing about F# but knew Haskell. So he was able to do a new game in his first week at work, which was a lot more than I managed to do at my next job, which was at Just Eat, where I had to spend a whole week just going induction. So the thing I found is that is when you transition to the F#, the difficulty is more in transitioning the thinking. And if you have a lot of experience with C# or Java, that doesn't necessarily help you because more than anything, you have to unlearn what you've learned before you can change your mindset to a different way of thinking. Whereas someone who's got experience with function programming, learning a different syntax is the easy part. Learning how to solve problems in a different way, that's often the hard part. And it took maybe 2 years for us to get to the point where everyone in the team is comfortable reading and working in the F# code to various degrees of competency, but at least everyone is comfortable working the code base. With one specialized guide, one specialist that basically build all the backends for all the slots. So one junior graduate is basically doing the work of a whole team of Java developers.
That's pretty awesome. You've touched a little bit on what question I was going to ask, which was, what advice would you have for somebody who's wanting to get started in F# or learn about it, but it's coming from a very heavy C# background? Sure.
I mean, C# is actually, you're not in a bad place compared to Java, because C# you've already had loads of functional features. Link, for example, is a good example. How we write code before and after link is completely different. Nowadays, we wouldn't think about doing all these for loops everywhere just to accumulate things and map things. We just use select and where, right? So you've got loads of exposure to some of this functional thinking already. But I think the difference is that because the default is still imperative, it's still mutable things everywhere. And that's where F# sort of guides you towards a different way of doing things, where the default is what it should be doing. So if you listen to a lot of the big OO guys, they also talk about all these things. Okay, immutability is important, and because it's concurrency and all these other reasons. But the language is working against you. The tools that we use in the language is also working against you. If you use resharper, you open bracket, straight away you get setter, almost without even asking for it. So that's one of the nice things about F# is that where you want mutability is down to you to do the actual work, so that you have to be conscious about the decision where you make of where the system, what parts of my system can change, what parts can't. And in terms of getting to F#, I would say find some problem that you have at work, maybe, or even some side projects, small things, and then just expose yourself to that. It would probably take time to change your mindset, but it will happen. You just have to take small steps at a time. Maybe don't try to rewrite a whole project, a critical system at work, because if you fail, then you're never going to see, no one want to hear about F# ever again. But if you try small things at a time and then prove that we can do this, then you have a better chance of succeeding in adopting F# at work. And also one thing I would say is that as someone who's gone through this and try to do this at work is because if you are the person driving it at work, then it's also down to you to really be the link to the community and to find out for the team, on behalf of the team, what is happening in the community, and also be the person to sort of take the fall when things doesn't quite work, and at least help people work through things. Because initially there will be loads of people saying, just why is this so difficult in F#? Why can I not have no's? So as a person to driving that change, there's a lot more that's a lot of burden on you, but the reward is well worth it, I think. Any other questions? Okay, if not, I'm going to be around tomorrow as well. It's kind of my bedtime for me. Cool. Thank you very much. Let's see.